Welcome back, chemists. In this video, we will be focusing on measurements and identification of significant figures. After today, you should be able to identify data as accurate or precise, identify the significant digits in a number, and demonstrate how to read significant figures off of measuring instruments. A measurement is really just a type of observation. When we look at measurements, we can say a measurement is very accurate. And when we talk about accuracy, what we really mean is how close a measurement is to the true or accepted value. So for example, if I were to take the mass of a 50-gram mass and I got a mass of 50 grams, that would be considered accurate. If I put it on the balance and got a mass of 32.18 grams, I would say that that is not accurate. And a mass of 49.99 grams is pretty close, so I would argue that it is accurate. You may sometimes also say that a measurement is precise. And precision really reflects how close multiple measurements are to each other. So if we take, again, the 50-gram mass and we put it on a balance and we get a set of data, the first set is going to be accurate and precise because you can see it's very close to the mass of 50 grams. It is 50 grams, and the mass is the same each time. The next set of data on the right shows that it's accurate and precise again because, again, they're pretty close to 50 grams over and over again. However, down below, you have data that is not accurate, yet it is precise. So if you look, it is not accurate because it is not close to 50 grams. However, it is precise because all of the measurements are identical to each other. They're very similar to each other. An easy way to remember is if you're confused about accuracy, I picture the C's in accurate representing the C in correct. The precision, the R in precision, represents the R in reproducibility, right? The ability to get the same measurement over and over again. Let's talk a little bit about significant figures. And so this is going to help us determine how many digits we should have in our numbers whenever we're working off of measuring devices. So whenever you're measuring something, there is going to be uncertainty in all of your measurements. All of the certain digits include all the numbers read directly off of the device plus one estimated digit, and that's where the uncertain digit comes in. So this is a graduated cylinder. The units of this is measured in milliliters. And so just by looking at this, you can see that you can directly read off of this graduated cylinder, and right where you see the bottom of that meniscus touching, this is definitely going to be 56. But then, according to our rules, we need to estimate. So our reading could be 56.0 milliliters. It could also be 56.1 milliliters. It could even be 56.9 milliliters. However, I would probably argue that your rounding or your estimation really needs some work. You probably need a little bit of practice. But in this case, I would say 56.0, 56.1 milliliters are all really good measurements. However, that last digit is uncertain and it varies from person to person. The amount of definite digits depends on the measuring device. And so an exact number is often said to have no uncertainty, and therefore it has an infinite number of sig figs. So whenever we're counting things, like 25 people, we're really talking about 25.00000. You get the idea. So that is considered an exact number, and that will never limit your number of significant figures in your calculations. But we'll come back to that a little bit later. Anytime you have defined quantities, such as these conversion factors, like 12 inches equal a foot or 100 centimeters equal a meter, those are considered exact and again, will not limit your number of significant figures in calculations. So here's how we identify significant figures. There's a bunch of rules. The first one's pretty easy. All non-zero digits are significant. So in the number of 2.17, there are 3 significant figures. In the number 3,894.6, there are 5 significant figures. Here's another rule. Leading zeros, or zeros that are to the left of the number, are never significant. For example, 0.003, the 3 is the only significant digit. The zeros there are there to indicate really a placeholder and indicate how small, in this case, the number is. This number, also, there's only one significant figure. Because those zeros are leading, the 4 is the only thing that is significant. Captive zeros, these are zeros in the middle of non-zero numbers, are always significant. So 205, that has 3 sig figs. That's 20,005. There are 5 significant figures there. Both sets of zeros are captive zeros. Trailing zeros are sometimes significant, and these are the numbers that appear at the end. So this one is often a very tricky rule for students, and especially because they feel it's a little ambiguous when it says sometimes. So let me show you the 2 different things that you want to look for to decide whether or not the zeros are significant. The first thing is they are going to be significant if the number contains a decimal point. So for example, 155.0. That 0.0 is considered significant. Also, it's a trailing zero because, right, it comes at the end of the number. So that 0 is significant, so therefore there are 4 sig figs there. 0.450, the 0 all the way to the left is not significant, right? That's just a leading 0. The 0 at the end, however, because there's a decimal point, means that it is significant. So there are 3 sig figs in that number. The other scenario is, you probably guessed it, they're not going to be significant if the number does not contain a decimal point. So in this number, 1550, that 0 is not significant because there's no decimal point. In the number 45,000, there's only 2 sig figs here because, again, there's no decimal point at the end there. So here's a really helpful summary for students. So the first set of zeros, these are called leading zeros. And again, they are never going to be significant. So you'll never count them whenever you're identifying the number of sig figs. The zeros in the middle are captive zeros, and they are always significant. So you're always going to count them whenever you're counting your sig figs. And then finally, these zeros at the end are trailing, and they are sometimes significant. If there's a decimal point, then they're significant. So can you count how many sig figs are in this number? Well, I count, let's see, the 4, the 2, the 4, all 3 of those zeros in green, the 6, as well as the zeros in pink. The hardest one out of all of these is going to be the zeros in pink, because that's always the one that kind of trips students up. So again, because there's a decimal point in this number, those zeros are considered significant. So I count 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures in this number. So let's try some examples. So how many sig figs are in the following? So in this first one, these are the non-zero numbers, so 3 automatically. Those zeros in number 2 at the end are called trailing zeros. Remember, those are sometimes significant, but only significant if there's a decimal. So that is also going to have 3 sig figs. This next one, there's captive zeros there. So that means every number in that number is going to be significant. So there's 6. In number 4, the zeros in front are leading zeros. Remember, they are never significant. So therefore, there's only 2. In the number 43,000, notice there's trailing zeros, but no decimal point. So there's only 2 sig figs. And then anytime you have scientific notation, the coefficient is always going to tell you the number of significant figures. So 1.09 tells you that there are 3 sig figs, which is kind of nice. It makes it a little bit easier to tell how many. So if you have any questions, you'll obviously want to talk to your teacher. Make sure you can check in with them. And at this point, you can begin worksheet 2H. Thank you so much for watching.